So here's our list of to-dos for this module. We're going to go over visuals, numerical summaries. We're going to talk about shape, outlier, center, and spread. And then in the next module, we're going to talk about regression, correlation, and scatter plots. To show you why we use visuals and numerical summaries when it comes to quantitative data, I want you to look at the table below. This table contains the average monthly stock price for the last 6 years before AGI had a little bit of a financial crisis. Now, at the end of every day, the price of the stock is recorded. So the prices in this table are the average across every month across these 6 years. So that's 77.26 in the upper left. That is the average price of the stock in the month of January across all 31 days in 2002. Now, if I was to ask you two simple questions, which month and in which year was the largest average price, and which month and what year had the lowest average price? I want you to take a moment and appreciate how simple those two questions are, but that the answers to those two questions are not immediate. You have to sift through this table and double check yourself to make sure you do have the largest and you do have the smallest. A question like that should take a few moments to answer, not a few minutes, like 5 or 10 minutes. Now, the first graph that we'll usually reach for in quantitative data is called a histogram. It looks very similar to the bar chart with one crucial difference. In a bar chart, there were categories or bins, and you would use the counts to tell how high the bars were in each bin or category. But here, there are no bins or categories, so we have to kind of make our own. So you notice on the bottom x-axis, I've labeled 45, 50, 55, 60. I've counted off by $5 increments, and those will be my bins. Once I'm there, I can just count up how many stock prices are in each bin or category, and then the height will represent the count. The only difference between these two is the one on the left uses the raw counts, and the one on the right uses the percents by taking the raw counts and dividing them by the total. Now, before I started making this graph, I first had to determine how big my intervals or my bins were going to be. I picked 5, but you could pick anything, $1, $2, $7, $10, and it's not that there's a right or wrong answer, but how big you want your categories to be will determine a little bit what your graph looks like in the end. So I've grabbed some data about salaries and I've made histograms, but with different sizes of bins. In the top left, I've used a bin size of $10, in the top right, $25, the lower left, $50, and the bottom right, $100. And now you can visually see the difference. In the upper left, where the bin size is small, you get the most amount of bars. So really fine-grained detail. You can tell the difference between even the smallest change in salaries. Where on the bottom right is the opposite. The bin sizes are very big, so you don't have that many bars, so you can't really tell much between the small changes in salaries, but it's very easy to see the big picture. The other two, the bin size of 50 and 25, are kind of happy mediums. So usually the way I go about deciding bin size is what kind of question I'm trying to answer at the time. If it's a large scale picture problem, I'll use a huge bin size just so I can get a really quick picture. If I have a really small fine-grained detail I need to know, I'll use a small bin size so I get the most amount of bars. Now, after we make the graph, our next step is to describe what we see. And there's actually a lot of characteristics that we're going to want to point out when describing an entire data set, and not just one particular thing. Misleading statements and misleading conclusions a lot of times come from leaving part of the story out. So when we're describing a data set, it's important to know what kind of things do you need to hit on to tell the whole story. This histogram came from another group of salaries, and as you can see where I marked out, the average is just under $58,000. So if I was to say the average here is about $58,000, that would be correct. But that's only telling some of the story here, because these salaries come from men and women. So if I wanted to tell a little bit more of a holistic story, I could make a histogram for the men and the women separately. And that's what I've done here. So you can see on the top that the men make on average $63,000, and on the bottom, women make an average of $50,000. Now, if somebody wanted to summarize this by saying that men make more than women, on average, that is technically true, but awfully misleading. Because although 63,000 is more than 50,000, there are a lot of women in the bottom graph that make a lot more than the men in the top graph. And honestly, there is a few women who have the highest salaries between both groups. A more holistic big picture description would also include how spread the salaries are. Yes, both groups have more lower salaries than not, but the women's salaries are a little bit more spread out, which means there are more women on the far right-hand side than there are men on the right-hand side. This is an example to show you that to describe a histogram with a single statement or single number in the best case scenario is extremely difficult, but worse is often irresponsible, because by doing so, you are missing out on some, maybe a lot of crucial details and only telling some of the story, not the whole story. This was a headline in 2024. It said workers with disabilities are paid 12% less per hour than other employees. Now, although that is probably technically true, I can't tell you, because there is no link to the data, that this is describing an entire data set with one number. They are not talking about the spread of the salaries, the average of the salaries, just that the difference of some groups, the two groups, workers with disabilities and ones are not, had a difference of 12%. Now, other than there was a 12% difference between these two groups, we know nothing else. We don't know if there were more salaries on the low side, the right side, the middle for each group. We don't know if that's different for each group. Maybe the disability workers had a lot of high salaries, but a lot of low salaries, so they averaged out in the middle, and maybe it was something different for the non-disability workers. We also don't know the salaries for both groups. If one group made 80 and another group made 70, that's a 12% difference. But so is $120,000 and $105,000. That's a 12% difference too. This headline from 2024 says that summer in that year was the world's hottest on record in the EU. So again, they're summarizing data with a single sentence. Now, they didn't post the data, but it is likely talking about the average temperature across those 4 months, May, June, July, and August. Just like the salaries and the stocks, the average for these months is made up of the day temperatures. But just by looking at the average, you don't know whether the day-to-day was very drastically changing, if it was around the same every day and that's what the average was, or again, if some were just absolute scorchers and some others weren't. And that wouldn't have to be the same month to month. It could be different for May, June, July, and August, and maybe the whole summer averaged out to something. Another thing to notice is they didn't tell you how hot that summer was on average, it was just the hottest. If the average temperature beforehand was 95 and this summer was 96, guess what? This summer is now the hottest. And although that is technically true, it would have been the hottest in that case, as misleading the same way that tweet about the high school diplomas is a little misleading. Yes, it is an all-time high, but all-time high without context doesn't give the entire picture and doesn't tell the whole story. To accurately paint the big picture of an entire distribution, there are 4 attributes that you need to describe. There's a short acronym that your book uses called SOCS, S-O-C-S, to help you remember these 4 attributes. They are shape, outliers, center, and spread. So we'll walk through what each one of these attributes are, how we measure them, how we describe them, and why they're important. The first attribute in SOCS is shape. And the first thing that we want to talk about when it comes to shape is the number of modes. A mode is simply a peak or a hump that you would see in the histogram when you graph the distribution. It's important to note here that when we say peak or hump, we're not talking about a single bar, more as in a group of bars. So in this particular histogram where I'm showing the weights of newborns, there is one bar that is the tallest, but generally speaking, if you were to zoom out and think of this as more of a mountain range, there would be one peak, and it happened to be in the middle this time. When there is one peak, like we see here, we call that shape unimodal. Uni for one and modal for mode. In this next histogram where I'm showing test scores from a class, you can see that there are 2 groups here, and they form 2 peaks or 2 humps. So in this case, we would call this bimodal. Bi for 2, modal for mode. Now, if you have more than 2 modes, you can go ahead and call it trimodal or quadmodal if you have 3 or 4. But at this point, it's very common to just call any graph with more than 3 modes multimodal, like the histogram you'd see here of the body masses in grams. Now, like in this histogram, it could be that there are no distinct peaks or humps. Yes, there is a bar that is technically the highest there on the right of these chest ratings. But if you were to take a step back and look loosely, that there is no general peak or hump. This shape is called uniform, a histogram where there doesn't appear to have any distinct mode, and all the bars are approximately the same height. They don't have to be exactly equal, but approximately the same height. Once you've covered how many modes there are, if any, when describing shape, you want to also mention if there's symmetry or not. In this particular histogram, if you cut a line, a dotted line down the middle, and you folded this graph in on itself like it was on a piece of paper, the left half and the right half would generally match up with each other. Is it exact? No. Is it pretty close? It sure is. When that's the case, we call this shape symmetric. If the halves don't generally match up with each other, then it's likely that you have one of the following two shapes instead. These two histograms showed here, left and the right one, are not symmetric. They have these what we call tails, the thinner ends of the distribution. Now on the graph on the left, there's that tail that shoots out to the left. And on the graph on the right, there is a tail that shoots out to the right. That is, if you were to try to draw a line down the middle and match the left half and the right half up of these histograms, those tails would not match up with anything. So we call these graphs skew to the left and skew to the right appropriately, the direction from which the longer tail stretches. You can think about the tails being arrows pointing in the direction of the skew. When it's pointing to the left, skew to the left. If it's pointing to the right, skew to the right. Once you've covered if there's any symmetry or skewness, we've talked about if there's any modes, then we move on to the next letter in SOX, O, which stands for outliers. Now, outliers generally require a lot of nuance to discuss and can be contextual in how we measure them and discuss them, a lot more than what just one or two slides can provide. So we'll wait for those specific instances to pop up, but for now what I want to say is that when I say the word outlier, I mean a value that stands away from the body of the distribution. Values like that can affect every statistical method that we'll cover in this course, and they're not always errors or mistakes. Sometimes they're the most important and most interesting part of your data. So regardless of where they come from or how we measure them, they aren't something we want to ignore. But because they're very contextual, we'll hit those specifics when those topics come up. The next letter in SOX is C, and that stands for center. That is, where does most of your data lie? Now, there are a lot of ways that we measure this. Some of them you've already heard of before, but the most common one that we'll use in this class is called the mean. The mean is simply when you take all the values in a variable and you add them up, then divide by how many values you have. So I've written that out in words here, sum of all values of the variable divided by the number of observations. And there is a symbol that you will see used in this class and other classes a lot, and that is X with a bar on top, or any letter with a bar on top. Now, the X with the bar on top is a notation we'll use a lot for the mean. But there's also notation that describes summing all the values of a variable and dividing by the number of observations. And that notation is here on the right. Anytime in this class you see the Greek letter sigma, which looks like a big capital E, that means to add. So sigma x means add the variable x. And then n is usually the letter we use when we deal with number of observations or sample size. So that notation on the right simply says add x and divide by how many observations you have. It's the instructions on how to find the mean. Now, the goal of center, the goal of the mean, is usually to tell you where most of the data is. And sometimes this works really well, and sometimes it doesn't work well at all. One of the pros of the mean is that it utilizes all of the observations in a data set. And not every calculation will. We'll perform some calculations that'll only use a few of the observations. Now, what that also means is that if some of those observations are outliers, or your data has skew to it so it's not symmetric, the mean might not represent where most of the data is at all. Sometimes it could be way too far to the left or way far to the right, depending on how not symmetric or how skewed the data is. To show you an example of what I mean by that, here's that histogram of the newborn baby weights. Now, most of the data is right here in the middle. It's symmetric, it's unimodal, and most of the babies weighed right in the middle, around that 7.4, 7.5, 7.6 pounds. Now, if we were to take this data and calculate the mean, it turns out you get about 7.5 on the dot, and I've marked that here in red. So this is an example where the mean tells you exactly where most of the data is, which is not always the case. For example, if you go to that bimodal data of the test scores and you were to calculate the mean would be right about 60. But here you can see that hardly anybody scored 60. Most of the people scored either between 20 and 30 or between 70 and 100. So here, if you just looked at the mean, that doesn't tell you where most of the data is at all, actually. It does a very poor job of describing where most of the data lies. So long story short, if your data is unimodal and symmetric, and again, it doesn't have to be exact, your mean will tell you basically where most of your data is. But if your data is not both of those things, and again, it's a matter of degree, not black or white, the mean can miss most of your data completely, just like in these test scores. This also stands as a very good example of why you want to use all four of those attributes when talking about a distribution to accurately paint that picture. Talking about the test scores by just using the mean isn't going to do it. It's actually going to be quite misleading. Hardly anybody scored 60. You would need to tell someone, well, look, the reason the mean doesn't tell you where most of the scores are is because it's not unimodal and it's not symmetric. You need to tell them about the shape. And you need to talk to them about any potential outliers and the very last letter of SOX that we'll have yet to cover. Now we have other ways of measuring where the center of data is, specifically when the mean isn't doing a good job. So if your distribution is skewed, has gaps, or contains outliers, often we'll use the median instead. The median is the number that cuts your data set in half. That is, if you ordered your data set from left to right or right to left, it doesn't matter. There's a number such that half of the data is to the left of that and half the data is to the right. That number that makes that split is called the median. Now, we usually say that the median is resistant to outliers because it is much less impacted by outliers than the mean is. And I'll show you some examples of that here moving forward. Now, to show you how to find the median, you first have to sort your data set from smallest to largest. So here we've got two small but effective data sets. So we would sort them smallest to largest or largest to smallest, it won't matter. And then we'll have to find the middle, the number that splits the data set exactly in half. Now, sorting data set number 1, the number 12 lies directly in half. That is, there are two data values to the left and two data values to the right. So 12 is the median. In dataset 2, it becomes a little bit trickier because there isn't a value that lies directly in the middle. 4 and 6 lie in a tie. So when we have that scenario, there's a few different things we can do. In this class, we will find the average of those two. So the average of 4 and 6, which is 5, will be our median. So we use the median instead of the mean when we have outliers to deal with or we've got skewed data. So those are pros of using the median. It's a good measure of center when skewness is afoot and we've got some outliers that could really affect what the mean is. One of the cons, though, is that the median only depends on the number of observations. That is, it doesn't use the actual values of the observations at all. And that could be a downside. So between these two very silly yet effective data sets, I have ordered them from least to greatest, they both have the same median, 60. 60 splits both data sets exactly in half. But both of those data sets are actually very different. The magnitude of the numbers on the right are far bigger, 500 and 600, as opposed to 90 and 100. But since the median only uses the number of observations, not the actual values, those don't factor into what the median is at all. 60 splits it in half, and that's the end of the story. So does the median tell the whole story here of where the center of the data is? Yeah, it could be better, right? But again, that's only part of the story. We should still be talking about the shape. We should still be talking about outliers, and we should still be talking about the very last letter of SOX, spread. Now, before we get to spread, I want to mention some relationships between some of the first few letters we've talked about. Shape and center have a relationship between the two. They are not totally different things. It turns out that when your data is symmetric and unimodal like the graph here is, the mean and the median will either roughly be the same or exactly the same depending on how symmetric the data is. On the other hand, if you have some skewness in your data, such as skewed to the left, the mean will be less than the median. And for skewed right data, the mean will be bigger than the median. Some of the reasons why this is, take skewed left for instance. Skewed left data is symmetric data that has an extra long tail on the left. So if you were to start with symmetric data, where the mean and the median are in the middle of the hump, but then you add a tail to the left, well, you're going to have to include those in the mean when you add up all the values. So you're going to get more of those values there on the left. So the mean will shift to the left. And the median is the same. The only difference is that the median doesn't account for the values. It only accounts that, hey, we've got more physical observations on the left-hand side, so we need to shift to the left a little bit more. So the mean and median both shift to the left, but the mean will shift more since it accounts for the actual values, while the median does not. The same is true analogously for skewed to the right. I want to show you this short example to show you that what we've talked about so far, shape, center, and outliers, are not enough to tell the entire story of a distribution. So take these two classes, 5 students each, and they both take the same exam. And here are their scores. Class 1 scores a 60, 70, 80, 90, and 100. And Class 2 scores a 79, 79, 80, 81, and 81. Now in terms of shape, it turns out that both of these classes are exactly symmetric. Not fairly symmetric, they are exactly symmetric. If you were to fold the data sets across themselves right on 80, they would match up each other perfectly. So 60 and 70 are equidistant from 80 that 90 and 100 are. And the same thing with 79, 79, and 81 and 81. Now we haven't went into the details for outliers, but none of these observations stand away from their distributions all that much. So all we have left is center. Now if you worked ahead, you might have already found the mean and median for both of these classes, and you would have found that they are exactly the same. And not only are they the same for both classes, the mean and the median are also the same. They are all 80. Now I had this in a previous slide, but it's worth saying that it is extremely difficult or often irresponsible to describe an entire distribution with a single sentence or number, even if you were to use the mean and the median both. Both of these classes had the same. If you said, hey, I had two classes and they both had a mean of 80, and you said, yeah, but what if the shape is a little bit off? Shouldn't you use the median? And I go, yeah, well, the median is also 80. So then you might jump to a conclusion and say, well, guess they did the same then, didn't they? When in fact, they did not do the same. If you looked at the raw scores of these two classes, they did very differently. You wouldn't be wrong by saying class 1 had the worst score. Is that technically true? Yeah. But did class 1 also have the best score? Yes, also true. Did class 1 and class 2 perform the same? I mean, technically on the average and the median, yeah, they performed exactly the same. But did both of the classes actually do the same holistically? No, they did not. The problem with that statement would be that you're not telling the whole story. Yes, by the center, they did the same. Yes, by shape, they did the same. Even by outlier standards, there's none that really stand apart from their distribution. So if all of those are the same for both classes, what's different here? The answer is the very last letter in SOX, spread. One of the easiest ways to measure spread in a dataset is by something called the range, where we take the maximum value and the minimum value, and we find the difference between the two. It's very simple, it only requires 2 of the observations, and again, very easy to do by hand if you had to. Now, being very simple to calculate is obviously a pro, but the fact that it only uses the 2 most extreme values in a dataset is almost always a con, meaning that no matter what's going on in between those 2 values, whether the data is all scrunched together or also spread out within those 2 values, this range that you're calculating would not take that into account. It literally takes the biggest and the smallest, even if they are by outlier standards far away from the body of the distribution, and only uses those 2. Take those class 1 exam scores again, but instead of person 1 getting a 60, say person 1 didn't show up, so they got a 0. The range here would be 100 points, the biggest minus the smallest. So if you were to say, hey, these scores, they were spread by 100 points, technically that is true, but that's really not telling the whole story here. Most of these exam scores were within 10 to 20 points, but it was the 0 that's kind of throwing that off. So I want to use the idea of range to measure spread, but fix up that we're not going to use the biggest and the smallest values, because those are subject to being outliers. If instead we scooted inwards and used 70 and 90 and said, hey, the difference between those 2 values is 20, so most of these scores were spread by 20 points, more or less. That tells a way more accurate story of how spread these scores are. That is, if we focus on the middle 50% of the data instead of the most extreme values, we'll not be fooled by outliers when we're calculating things like spread. So that's what we're going to do when we calculate spread. We will find the 2 numbers that capture the middle 50% of the data. They are called quartile 1 and quartile 3, respectively. Once we've got those 2 numbers, we're going to take the difference between the 2. We'll call that the interquartile range, and that will tell you how spread your data set is. And this is not affected by outliers now. So as a small example, I have this data set here that I've ordered from least to greatest, and I have found the first and third quartile. You might be wondering, where is the second quartile? We also call out the median, so that is Q2. So the difference between the third quartile and the first quartile, which here are 9 and 4, happens to be 5. 9 minus 4 is 5. Now, in terms of describing spread, does 5 describe how far off these numbers are from each other? And I'd say generally speaking, yeah. Now, kind of like when finding the median, finding Q1 and Q3 can be a little tricky depending on how many data values you have. So I want to walk through two examples to show you how we'll do it in this class, since there are a lot of ways you can actually go about doing this. So the way I'm about to describe is called the Tukey method. It doesn't matter that you know that this is called the Tukey method. It's more important to know that this is how we're going to do it in this class. So step one is to sort your data set from smallest to largest. Step two, you're going to find the median and divide the data set in half. And here lies the tricky bit. When you do that, if you have an odd number of data values, you are going to include the median in both of the halves. So here in dataset 1, I have ordered them. There are an odd number of data points, so 9 is the median exactly. But if I was to go split that dataset in half, which half would 9 be in? Or should we exclude it altogether? And the answer for us is going to be we are going to include it in both the upper half and the lower half. The last step to find Q1 and Q3 is to simply find the median of those halves. So the lower half is 1, 4, 7, 8, 9, the median of which is 7. That is Q1. The upper half, 9, 13, 15, 20, 25, of which the median is 15. That is Q3. The difference between Q3 and Q1 is your interquartile range, which happens to be 15 minus 7, or 8 in this example. In dataset 2, we have an even number of data points. So the median isn't in the actual dataset, it's the average of 9 and 13. So when you go to split in half, there is no ambiguity of how to do that. The lower half is 1, 4, 7, 8, 9, and the upper half is 13, 15, 20, 25, and 30. There's no question of where the median goes because the median isn't a data point. It's halfway between 9 and 13. So the median of the lower half here, 1, 4, 7, 8, 9, is 7. The median of the upper half, 13, 15, 20, 25, and 30, is 20. So 7 and 20 are Q1 and Q3 respectively, and the interquartile range is the difference, which gives you 13. Now, a small warning moving forward. This is the method we're going to use in this class. That is called the Tukey method, and that's where we take the median and we include it in both the upper half and the lower half when the median is a data point. But that's not the only way to find Q1 and Q3. We could have excluded the median altogether. We could have only included it in the upper half, only included it in the lower half. There's actually a slew of combinations of ways to find Q1 and Q3. There's a software that I routinely use called R, and R alone has 9 different ways to compute values like this. So although there are a lot of ways, we all need to come to the same answer and have that consistency in this class. So we are going to use the Tukey method, the one where you include the median in both halves. So if you're going to be using any technology to work on homework or a project outside of this class, like your TI-84, TI-89, or Excel, or JUMP like we'll use, you're going to want to know which method you are using, so in case you run into some different answers, you know why that might be. All right, now that we've covered all the letters of SOX, shape, outliers, center, and spread, with a large asterisk on outliers because that's going to be contextual moving forward, is I want to show you a common visual that we'll use to help us describe a lot of these concepts of SOX, shape, outlier, center, and spread. And one of the most common ones is the 5-number summary and the graph that goes along with it. So the 5-number summary often includes the median, Q1, Q3, and the min and the max. Now we like to use the 5-number summary because just with 5 numbers, it tells you a lot of what SOX requires. You have the median, so you know the center. Even if your data is slightly skewed, the median does a pretty good job of telling you where the center is. You have Q1 and Q3, so you know the interquartile range, so you know spread. And you know min and max, so you can get an idea if you've got any outliers on the large end or the small end. Really, the only thing you're missing here is shape. There's really not a great way to tell shape here. And that's where putting this on a graph is really going to come into play. The graph or visual we use for the 5-number summary is called the box plot. Here on the right, I've got a box plot that is standing vertically, so I want to go over real briefly the different components and how we can use it to tell shape, along with the other things that 5-number tells us, center and spread and outliers. Now the first component to the box plot is the box itself, here which stands vertically, so you've got the top edge and the bottom edge. They are Q3 and Q1 respectively, so that box tells you where the middle 50% of your data is. So if that box is rather short, that means the middle 50% of your data is within a pretty tight range. If the box is very wide or very tall, the middle 50% of your data spans a quite big range. The line that lies inside of the box marks the median. Now, if the median is directly in the middle, that is a sign of symmetry. If the median is closer to one edge or the other, that is a sign of skewness. So here our median is a little closer to Q1, so that is a sign of skewness. The next component I want to point you to are the lines that extend from the top and the bottom of the box. We call these whiskers, and I'll go over how to make them here in a minute. But if they are the same length, roughly, that is another sign of symmetry. If they are a different length, that is a sign of skewness. Now, if there are outliers present, again, we'll go over here for the first time on how we judge what an outlier is going to be in this type of a graph. They'll be marked with a symbol, either circles or stars in this case. But regardless of whether there are circles or stars, we'll mark those as outliers. Observations that stand away from the body of the distribution. Now, in a box plot, how we determine which observations are outliers and which ones are not is they will be any observations that are outside of what I call the upper fence and lower fence. They are lines in the sand, more or less, that lie at 1.5 times the IQR above Q3 and 1.5 times the IQR below Q1. So they are limits or bounds that depend on the spread of your data set. So again, any observations that are outside of those bounds, we will mark as outliers. Now in this graph, we use stars and circles, but how you mark them is less important as we will mark them. Now the upper and lower fence will also help determine where the whiskers are going to go, because the whiskers are going to reach out from the box to the most extreme values that are not considered outliers. So the points that are furthest away from the box, but within the upper and lower fence. I've attached these 3 box plots in the bottom to 3 histograms at the top to show you how shape and center plays a role here. So when the median is in the middle of the box plot, you have symmetry, which if you look at the histogram, looks very symmetric. You can kind of fold it in on itself. If you've got a median that is to the left, and you've got this whisker that shoots out to the right, that is analogous to a tail that is going off to the right. So that would be skewed to the right. And analogously on the graph on the right-hand side, you've got this tail that's shooting off to the left, which is a whisker that is extending to the left. That will be skewed to the left. So now that we've went over all the components of a box plot, let's walk through describing one step by step using SOCs: shape, outliers, center, and spread. Now, this is a data set that has the app downloads separated by AM and PM for a large app. And the CFO of this app wants to know when people are downloading their app. So they have the number of downloads per hour over the span of a day, and they've separated them between AM and PM. So they went ahead and made some side-by-side box plots for the AM and box plots for the PM, to help describe what the difference between the 2 sets of downloads are. So here are those box plots. So what I want to do is walk through what describing SOCs would look like. And you don't have to do it in order, so I'll describe to you one way to go about doing this. My first statement is more of a general takeaway. And so here I say that there are generally more downloads in the afternoon than in the morning. And the reason I say that is that the green box on the right is for PM, the purple box on the left is for the AM, and the entire box, as an entirety, as a whole thing, is higher up than the AM box. Now I'll move on to SOCs, and I'll start with center. In the box plot, the line inside the box is the median, so I'm going to compare the medians. For PM, the median seems to be around that 22 mark, and the AM box seems to be around the 14 mark. So I state, the median for the number of afternoon downloads is around 22, as compared with 14 for the morning. Next, we'll move on to spread. And in the box plot, we like to use IQR for that. Since the top of the box is Q3, and the bottom of the box is Q1, the size of the box is literally the size of IQR. So I say here on the right for PM, the size of the box is a lot smaller than the purple box for AM, so the spread is smaller for PM than it is for AM. And as an extra side note, just as a size comparison, the entire box plot, that is including the whiskers for PM, is about the size of the box alone for AM. So again, just a comparison for the size of the spread in AM to PM. Moving on to shape, I say that the AM downloads appear slightly skewed. That's because the whisker in AM on the top is way longer than one on the bottom. As opposed to PM, it seems fairly symmetric. The median seems to be in the middle of the box. The whiskers aren't exactly the same length, but they're definitely not as different as AM, so more fairly symmetric as opposed to AM. And then finally, for outliers, in the box plot, outliers are notified by dots. Since there are no dots, there appears to be no outliers for AM or PM. And with that, we've covered all 4 attributes in SOC. We did shape, we did outliers, center, and spread, along with the general statement. And so I want you to notice that these statements aren't a statement of why things are the way they are, just a descriptive, here's what they are. Here is what the shape is, here is what the center is, are there outliers, yes or no, and here is what the spread is. Now we're not done talking about spread quite yet. We've talked about IQR, and that's a good place to start, especially for the box plot. But IQR only uses 2 data points and ignores the rest. So if the rest of the data points are really spread or not spread at all, that may not be picked up by IQR at all. Take this data set for example, some exam scores from this class. So you got the first 4 scores, which are 20, the next 4 which are 90, and nothing. If you found the IQR, you'd find that Q3 is 90 and Q1 is 20, these particular scores, and the IQR would be 70. That is, the spread of these exam scores seems to be 70. Now, is that telling you the whole story? No, not really. There are really 2 groups here, and within each group, there is no spread. But IQR doesn't account for those other data points. It only looks at Q1 and it only looks at Q3. It happens to be that the rest of the data points don't have any spread across the 90 and across the 20 scores. So what we would want alongside IQR is another way to calculate spread, but utilizing every data point, not just 2. And that's where variance and standard deviation come into play. These are words you may have heard before, maybe not. Regardless, these are 2 ways to measure spread that use every data point, not just 2. And we'll often write variance as S with a square on it, and we'll write standard deviation with an S without the square. So how do we calculate something like variance and standard deviation for that class of exam scores where they were 60, 70, 80, 90, and 100? What I'll do is I'll write below how we would calculate for this class, and then above that I'll write the general notation, which will build the formula for variance and standard deviation. Our first step is to calculate how far each one of those scores is from the average. So I'm going to take 60 minus 80, 70 minus 80, 80 minus 80, 90 minus 80, and 100 minus 80. How far is each exam score from the average score of 80? We call these deviations. That is, how far does a score deviate from the mean? And your intuition might tell you to add these up. Say, how far do these deviate in total? But there's a problem with doing that, because some of these are going to be positive and some will be negative. So they could cancel each other out, telling you that there is no spread at all, when in reality, there is quite a bit of spread. Now, there are a lot of things we could do to make these deviations positive, but we're going to square them for a lot of reasons. Many reasons moving down the road, it's going to solve a lot of other problems for us. But for now, just squaring is easy enough and it solves our issue right now. So we call these squared deviations. So now we can go ahead and add all of these up, and that would tell us how much these all deviate from the mean in a squared sense. But what if we wanted to know how much do they deviate on average? Because, some of them are going to be far away and some will be close. So on average, how far do they deviate? And if you're going to find the average, you would just divide by how many deviations you had. Now, to solve more problems moving forward, which we will get to right around Module 5 and Module 6, we are going to divide by how many observations or how many deviations we have, minus 1. So if we have 5 exam scores here, instead of dividing by 5, I'm going to divide by 4. Now, this is still, in a sense, an average amount of deviations, but the 5 versus 4 is going to solve some problems for us moving forward. So it's always 1 less than we started with. So instead of 5, we'll divide by 4. So this value of 250, that is what we call variance. That is the average of the squared deviations from the mean. So in a sense, how far on average were we from the average in a squared sense? Now, although this is a good step in the right direction because we've used all of our data points now, since we've squared all these deviations, the units here are not what we would have started with. Because, again, we've squared everything. So if the units were dollars, now these are squared dollars, which in some cases doesn't make any sense. but we've got a fix for that too here in just a slide or two. So if you wanted to use some of our new notation to write out what we just did, you would have the formula you see down below. Each x, an observation, minus the mean, x with a bar on top. We call that the deviation. We will square that for all of them and then add them up. That's what the sigma stands for. And then to find an average of sense, the average deviation, we'll divide by how many we have minus 1. We do the minus 1 to solve problems for us down the road, which we'll get to in about module 5. Now, since we squared everything, in the classroom example with those exam scores, variance would be 250. But on average, these scores were 250 away from each other. But that's so big because we've squared everything. So to get those units back down to the magnitude we started with, so taking the square root of 250 gives us 15.8, and those are in the units we started with. And if you look at the exam scores, are they about 15 points away from each other? Yeah, more or less they are. But now we've used every data point in the data set. We haven't excluded any. That value is called standard deviation. It's the square root of variance, and it measures spread of a data set that is in the same units that we started with. Now, just like IQR, the way variance and standard deviation work is that the bigger the number equals the more spread, and the smaller number equals less spread. So here are two histograms. One has a standard deviation and variance of 30 and 900, and the other has a standard deviation and variance of 7 and 49. Now, without context, those numbers don't really mean anything to you or me, but we can use them as a relative comparison to see which one has more spread. The variance and standard deviation are bigger for the graph on the left, so it has more spread. And if you look at the histogram, that is exactly true. It literally is spread out more than the one on the right. The last thing I want to cover in this section is how to compare individual observations, which will also give us another way to calculate outliers. So to go over that, I want you to imagine these two people, Chris and Amber. Now they both took a standardized test, but they took different tests. Chris took the SAT, Amber took the ACT, and their scores were 2,000 and 30 respectively. Now, it's pretty difficult to compare those scores directly because they're on totally different scales, and you might not be aware about some of these tests end up being harder than the others. So how are we supposed to know who did better on what? You might be thinking, well, just take the percentage, 2,000 out of 2,400 and 30 out of 36. But you'd find that they give you the exact same percentage. So again, how are we supposed to compare these two test scores that are totally different tests and the point values aren't very analogous either? And the answer lies in SOX, shape, outliers, center, and spread. So here's the histogram of the SAT scores. You can see that the shape is relatively symmetric. It is unimodal. The center, the mean, is 1,500. So 1,500 happens to be right in the middle of that peak also, since it's symmetric. And the standard deviation is 250. That is, on average, the distance from a score to the mean is 250 points. Now you can see Chris's score, 2,000, is way off to the right. So you can see actually, just by looking at the graph, Chris did pretty good. Chris did better than most people did on this exam. Here is the histogram of the ACT scores. Also symmetric, also unimodal, so that's shape. The center, the mean, is 24, and 24 happens to be right in the middle of the peak again, since it's symmetric. And the standard deviation is 2. That is, on average, a score is 2 points away from the mean of 24. And I've also marked out Amber's score way out on the right. Now you can see with Amber's score, Amber not only did really well, she did exceptionally well. There aren't many people who did better than she did. There are some, but man, not many. To account for the mean and the standard deviation, the center and the spread of these exams, we are going to answer this question. How many standard deviations from the mean was Chris, and how many standard deviations from the mean was Amber? That way, we'll compare Chris to the rest of the SAT scores, and compare Amber to the rest of the ACT scores. And since it'll be in terms of standard deviations, we'll be able to compare them directly, because it won't be out of the point totals anymore. So looking at Chris first, Chris's score of 2,000 was 500 points above average. That is 2,000 minus 1,500. And since a single standard deviation is 250, that would make Chris 2 standard deviations above the mean. That is 500 divided by 250 gives you 2. And like I said, that looks like it's pretty good, because if you look at the graph, Chris did better than most people. There are some who did better, but not many. Now if you rinse and repeat that for Amber, Amber was 6 points above the mean. That is, her score of 30 minus the mean score, 24, gives you 6. And since a single standard deviation is 2, that makes Amber 3 standard deviations above the mean. That is 6 divided by 2 gives you 3. And as you can see, as in the histogram, that's not only really good, that is exceptionally good. There is hardly anybody above 3 standard deviations above the mean. So these two numbers that we just calculated for Chris and Amber, we can compare directly because they have the same units. They are how many standard deviations above the mean they are. And Amber is further above the mean than Chris is. So although Chris did very good, and I would be happy to have Chris's score, Amber did better. Amber did better on the ACT than Chris did on the SAT because we took into account the center and the spread. This value is what we call a z-score, or a standardized value. How many standard deviations is an observation away from the mean? Not only does this give us a way to compare observations with totally different units from totally different data sets, but it gives us a now new idea of what it means to be away from the average. In other words, if you're 3 standard deviations above the mean, that's really far. Amber's score was exceptional. There was hardly any data points past that. And so if you got more than 3 standard deviations above the mean, or 3 standard deviations below the mean, that will be another line in the sand to determine what an outlier could be. I'll walk through one more short example using z-scores to show you how we can use them to compare data values with different units. So say that we're looking at houses, and we've got 350 recent sales. And between these houses, the average price was $175,000 with a standard deviation of $55,000. But we also know the size of the houses. On average, they were 2,100 square feet and a standard deviation of 650 square feet. So now let's compare 2 houses. One house that was $340,000 and a second house which has 5,000 square feet. Which of these houses would be more unusual? Which of these houses would be further away from average? So to answer that question, we will compute the z-score for both of these houses. For the house that costs $340,000, we will subtract the mean and divide by the standard deviation. So 340,000 minus 175,000 divided by 55,000, which will give you 3 on the dot. So that house would be 3 standard deviations away from the mean. That would be the z-score for a house that costs $340,000. For the house with 5,000 square feet, we will do the same. We will subtract the mean and divide by standard deviation, but for square footage this time. So 5,000 minus the mean, 2,100, divided by standard deviation, 650, which will give you 4.46. So that house was 4.46 standard deviations away from the mean. And that would be its z-score. So in this case, a house with 5,000 square feet is more unusual. It's further away from average than a house that costs $340,000. Even though they have different units, we compared their z-scores because they have the same units. The number of standard deviations are the units. Now, it's not that they're positive that makes them unusual. It's how far from average they are. So for example, if we had a house that had a z-score of negative 5.5 standard deviations from average, that would be more unusual than both of these. Not because it would be the biggest, because it wouldn't be, it would be negative, but it would be furthest from average. 5.5 standard deviations below is further away than 3 above and further away than 4.46 above. It's just in the opposite direction. In other words, the further away a z-score is from 0 means the more standard deviations that observation is away from the mean, which means that is more unusual of an observation.